Okay, today brought to you by the letter E. Just kidding. Okay, so we're going to do e to the x properties and derivatives, just in case you all forgot about e to the x properties. Okay, so we know that the function ln of x has an inverse because it passes the horizontal line test. So ln of x has a domain of, it passes through the point 1 comma 0, and it has the domain of x is greater than 0. Okay, it passes the horizontal line test. And so the inverse of ln of x is the exponential function e to the x. Because they are inverses, then these two properties are true. That the composition, so if we said f of g of x is equal to x, and g of f of x is also equal to x. Okay, my dog has things to say about that too. Okay, so next, let's just solve these two logarithmic and exponential functions. So remember what we do is we take the log of both sides, which because it's a base of e, I'm going to take the ln of both sides. So I get the ln of 7 is equal to the ln of e to the x plus 1. Power property says that I can rewrite this as the x plus 1 times the ln of e, and e to the e is just 1. So I can subtract 1. So I get the ln of 7 minus 1 is equal to x. Okay, what we also have seen in the past is another way to do this would be to snail, right? What I get is the ln base e, ln has a base of e, so of 7 is equal to x plus 1, then subtract 1 from both sides, so I get x is equal to the ln of 7 minus 1. Same. Okay? All right, so number 2, we're going to do, what I can do is I can snail. So remember there's a base of e. So I'm going to go to the exponent and then switch back to the number. So I get e to the 5 is equal to 2x minus 3. Solving for x, I'm going to add 3. So e to the 5 plus 3 is equal to 2x. Divide by 2. E to the 5 plus 3 over 2. And that's that. Okay, a couple properties. If I have e to the a times e to the b, using our exponent properties, that would be e to the a plus b. And then e to the a over e to the b, exponent rules, the base is e, and I'm subtracting the exponents, a minus b. Quickly, let's do these 3 examples. I got e to the 4 times e to the 2, which gives me e to the 4 plus 2, which is 6. The second example, we're going to quotient property of exponents as we subtract exponents, so e to the 3. And then e to the 1 minus 5 would be e to the negative 4, or 1 over e to the 4. Okay, so some properties of our natural exponent function, so e to the x. Okay, I have it listed here in blue, e to the x. So the domain is all real numbers. The range is x is greater than 0, right? Because our asymptote is at 0. E to the x is always increasing, and it is continuous, and it is concave up on the entire domain. Okay, we can see that the limit as x goes to negative infinity of e to the x gets close to 0, so it approaches 0, and that, oh, I put to change this in my notes and I didn't. So as the limit as e to the x approaches positive infinity, we are going to a y value of infinity. Okay. Next up, let's learn how to take the derivative of e to the x. I told you this a long time ago. I don't expect you to remember this, but the derivative of e to the x is e to the x. It means that the output of e to the x, so the y value of e to the x, is actually the derivative value at a point as well. So cool. Okay, so if I have e to the u with, I'm taking the derivative with respect to x of e to the u, this would be e to the u times the derivative of the chain, so du dx. Or you can write that as e to the u times u prime. All right, let's do a couple. So let's differentiate d over dx. So we're going to do d dx of e to the 2x minus 1. This looks like chain rule. So what's great is that we remember that d dx of e to the u is equal to e to the u times u prime. So everything's going to stay the same here. I get e to the 2x minus 1 times the derivative of the inside, which is 2. And that is that. I guess we can make it prettier. 2e to the 2x minus 1. Okay, number 2. So again, same thing. We have e to the, everything's going to stay the same. So e to the 3 over x times the derivative of negative 3 over x can be rewritten as negative 3x to the negative 1. So when I take the derivative of that, we'll call that u. U prime is equal to, we multiply, so 3x, and then we decrease the power to the negative 2. So times 3x to the negative 2. Let's just write it nice. It's 3e to the negative 3 over x, all over x squared. I guess I can write this a little different. 3 over, since we have a negative exponent, to be e to the 3 over x times x squared in the denominator. Okay, all of these are acceptable. Number 3. So this looks like product rule to me. So lefty right, righty left. I'm going to write left is x squared, d right. So e to the 4x times the input or the chain times 4x plus right, e to the 4x times the derivative of the left, so 2x. And I just, again, write it in a little bit nicer form. I get 4x squared e to the 4x plus 2x e to the 4x. I guess technically you could factor out an e to the 4x, but I'm going to stop there. Okay, we're going to do a little situation here. Okay, the projected population Y in 10,000s of California from 2015 to 2030 can be modeled by Y is equal to 34,696 e to the 0.0097 t, where t represents the years, with t equal to 15 equaling 2015. So t equals 0 would equal 2000. T equals 30 would equal 2030. And we're going to figure out the rate which the population will be changing in 2020. Okay, so right away, I'm like 2020, that is t is equal to 20. I'm just going to write it so I don't forget right now. Okay, so, and it's a population, the rate of the population changing. So I know that was going to be dr dt. Okay, so, or y prime, it's the derivative. Okay, so I have an equation, y in terms of t, so dy, so I guess it's not dr dt, it's going to be dy dt, because it's the derivative with respect to time. Okay, so we need to take y, 34,696 e to the 0.0097 t, and take the derivative. All right, so I have 34,696, and then I'm going to take the derivative of this, which is e to the 0.0097 t times the chain, which is 0.0097. Okay, and I get y prime is equal to 336.5512 e to the 0.0097 t. Okay, so that is my derivative. And then I want to evaluate y prime of 20. So 336.5512 e to the 0.0097 times 20. And when I evaluate that, I got 408.605 truncated, or 408.606 rounded, and this is in thousands. This is thousands of people per year. All right. Fun times. Moving on. Our last example for this video, and then there'll be another one. Okay. So we're going to take d dy of y squared is equal to 2 times e to the xy. So I see implicit differentiation here, since y is not by itself. Okay, could you make y by itself? Yeah, but I think I'm going to use implicit differentiation. It seems easier. So the left, 2y times dy dx is equal to 2e to the xy. So everything stays the same. Then we have to take the derivative of the inside, okay, which is x times y, so lefty right. So right here, this is product rule. Left is x. The derivative of y is dy dx, plus the right, which is y, times the derivative of x, which is 1. Okay, so I get 2y times dy dx is equal to 2e to the xy times x dy over dx. Actually, I'm going to distribute. Okay, so I got a little crazy with the eraser there. Okay, so I get 2e to the xy times x dy dx plus 2e to the xy times y. Yeah, that's nice. Okay, let's get all of our dy dx's on one side. So we're going to subtract 2ex to the y times x dy dx minus 2e to the xy times x dy dx. So we get negative 2. Actually, yeah. Okay, so I get 2y dy dx minus, I'm just going to make this look nicer, 2x e to the xy dy dx is equal to 2y e to the xy. Yeah, I like that. Okay, let's factor out a dy dx. So dy dx times 2y minus 2x e to the xy is equal to 2y e to the xy. We're almost there. Then divide both sides by 2y minus 2x e to the xy. And that is it. Dy over dx is equal to 2y e to the xy over 2y minus 2x e to the xy. I suppose we could substitute out the y if we wanted to, but I don't see a need right now. So I'm going to leave it. Okay. Stay tuned for e to the x integration.